So now it's time for Max Fathi's talk from Université Paris, and he will talk us about Caffarelli's contraction and entropic regularization.
Thank you very much. So thanks, Leonard, and thanks to the organizer for the opportunity to speak here. So yeah, same as with Jan, if you have any questions during the talk, please don't hesitate to interrupt, to speak. I would hope this will be as interactive as possible. So what I will talk about today is a proof of the Caffarelli contraction theorem, which is a result about global regularity for optimal transport maps between certain measures that satisfy certain convexity conditions that I will describe during the talk. So it's based on joint work with Nathalie Gozlan, who is also here at the Université de Paris, and Maxime Prodhomme, who's a PhD student in Toulouse. So I didn't prepare the first slide because I thought Jan will say all I wanted to say here before, and indeed he did. So but maybe just in case I will kind of repeat some of what he said at the beginning of his talk. So what's the optimal transport problem? So we have a pile of sand and some ditch, and we want to fill the hole with the sand, and say, assuming that the hole and the pile of sand have same volume. So we have some unit mass of sand at some point X. We send it somewhere, and the cost to move the mass from some point X to a point Y, there's a certain cost. It depends on where you started from. It depends on where you arrive. And then you want to choose an allocation. So a way of allocating mass from a point X to Y is you can modelize it by a coupling, pi of X, Y, which is the proportion of mass you want to send from X to Y. And of course, for this to make sense, you have a problem of marginal constraints. So the first marginal, let's say when our RD, has to be fixed by the distribution of your initial mass, so which is going to be given by some positive measure. And without a loss of generality, we can assume the total mass to be 1. And the second marginal should be the distribution wherever you arrive, which we also represent by some measure. And now the optimal transport problem, giving a cost, is over all possible ways of allocating mass from the starting distribution to the target, you minimize the total cost of your move. So the total cost is the average of your cost function with respect to this coupling. And we want to minimize over all possible couplings, but with these given marginals. And this gives us an optimal transport cost. And in this talk, I will almost always only be interested in the quadratic cost, which Jan mentioned at the beginning of his talk. So for convenience, I'm adding a factor 1/2 in front, but this is just for convenience. It's of course, it doesn't change anything in the structures of the optimizers. And it turns out that in the case of the quadratic cost, the optimal transport, the optimal coupling, has a very specific structure, in that it is as soon as the first measure mu is absolutely continuous, it has a density with respect to the Lebesgue measure, the optimal allocation is deterministic. Every mass at some point X is sent to a unique point. We do not split mass. And so we can represent our optimal coupling by some function t. So pi is going to be the push forward of mu by the map identity t. So of course it's a measure on the product space, but it's entirely deterministic, and that is the push forward of mu by some deterministic map. And moreover, the map T, which we often call the Brownian map, this basic result is due to Brownian and was then generalized by McCann. And moreover, this Brownian map T arises as the gradient of some convex function. And moreover, it is actually unique in that up to a constant, there is a unique convex function from which an optimal transport map may arise, and it's the only it is the unique optimal coupling, this coupling pi. So what I will talk about today is about global regularity in a particular setting for this optimal transport map. Okay, so this map T, it solves a PDE just because of the change of variable. Indeed, if we average out some test function f in just the first variable, f of x d pi of xy, because of the marginal constraint, this is f d mu. And then for some other test function, g of y d pi, this is going to be equal to the integral of g with respect to nu. But it's because of the structure of the optimal transport map, it's also the average of the composition of g with the transport map with respect to mu. So T induces a change of variable between mu and nu. So we can write the change of variable formula for this. And then it happens when we write down the change of variable formula. What do we get? We get that the optimal map must solve in a weak sense a Monge-Ampère PDE. So this is if we write e to the power minus w and e to the power minus v for the densities. I'm assuming here that both have densities. This is the PDE that the optimal transport map has to solve. And because we know it arises the gradient of the convex function, we can write it as a second order fully nonlinear PDE, Monge-Ampère type. Okay, so then, and it happens that because of uniqueness of optimal transport maps, the two descriptions are completely equivalent. We can view a quadratic optimal transport problem as an equivalent way of describing convex solutions of these PDEs. And the two viewpoints are, at least when we have densities, the two viewpoints are completely equivalent. Okay, and now as I was saying, I will be interested. Okay, sorry. First, I want to talk about, before talking about regularity, I want to talk about the dual description of optimal transport. So here we introduced the optimal transport problem as a minimization problem over a set of probability measures. And we have duality between measures and functions. And by duality, we can often write minimization problems over sets of measures as maximization problems over sets of functions. And there are broad techniques for doing this, but in the particular setting of the optimal transport problem with quadratic cost, this is the formula that arises. So we minimize 1/2 of the quadratic cost over all possible couplings with fixed marginals mu and nu. And we can rewrite it as maximizing a sum of two integrals, one with respect to mu and one with respect to nu over all functions phi. And we take some function phi and we average 1/2 of x squared minus phi with respect to mu, and we average 1/2 of y squared minus phi star with respect to nu. And the two descriptions are equivalent. The minimal cost over all couplings for the quadratic cost is the maximum of the sum of two integrals over all functions phi. And it happens that, okay, so here phi star is the Legendre transform of phi. And this Legendre transform is an order reversing involution on convex functions. So it happens that we can restrict ourselves to convex functions. And because we only care about the supremum, this only makes things better. And it happens that the optimal function phi in this dual formulation is exactly the convex function from which the optimal transport map T arises. So there exists some function phi for which this supremum is attained. It's a convex function, and it is precisely this convex function whose gradient gives the optimal transport map from the Broglie theorem. And now it can look like this description breaks the symmetry between mu and nu, because on one hand we have average of phi, and on the other integral we have the integral of this Legendre transform. But because the Legendre transform is an involution on convex functions, we haven't really broken the symmetry. And as soon as both measures have a density, the gradient of phi star is going to be the inverse transport map. It's the map that's going to be sent nu onto mu. So there is it can look at first glance like we're breaking the symmetry, but no, we're not. Okay, so this gives a dual description, which I'm going to talk a bit again in the sequel. But now I want to state the theorem I want to prove. So it's a 2001 theorem by Caffarelli, which states that if your first measure mu is a standard Gaussian measure, and the target measure, sorry, this is not, forget about this one. And if the second measure nu is a what we call uniformly log concave, so it has a density, and the log of the density is uniformly concave. So we write it as e to the power minus v, and the Hessian of v is bounded from below. So here I'm bounding it from below by the identity matrix in the sense of quadratic forms. And then it turns out that if we transport, so this is a class of such measures, we can think of them as being more log concave than the Gaussian measure. The Hessian is even larger than the Hessian of the Gaussian potential. And what the Caffarelli contraction theorem states is that the optimal transport map sending the Gaussian onto such measures is going to be globally one Lipschitz. So the constant one here is the constant one in front of the identity matrix here. We could do a more general version, which I will address later on, but let's stick with this one to reduce notations. So we have.
May I ask you a question?
Yes, of course.
So if you begin with mu, you end up with nu, and then you get Caffarelli's theorem. Can you do it in the other way? Beginning with mu and ending up with mu?
I will talk about the results in the other way around, but at the end of the talk. I want to stick with one with the example with the fewest amount of parameters when I explain the proof. And then at the end of the talk, I will explain the more general version where we reduce where we consider more general starting measures.
Thank you.
Okay, and so we have this idea that, okay, if we send a Gaussian measure into something that is more log concave than the Gaussian, then it's a contraction, or globally one Lipschitz. And the original proof of Caffarelli has essentially nothing to do with optimal transport. It's really only relies on the Morgan-Pair formulation here, and it's based on the maximum principle. So he applied maximum principle to this PD to get a global estimate on the largest possible value of the operator norm of the Hessian of phi. And the goal of what I will talk about today is to present a proof that doesn't use Morgan-Pair PD at all, and instead relies on the optimal transport structure. And the main motivation, I will not present results in that direction, but the main motivation is to have a strategy of proof that could conceivably apply to other costs or other geometries where the link with PDs is harder to use. Okay, so before talking about the proof, I want to talk a bit about why we were interested in having globally Lipschitz transport maps. And the main application is that it provides a convenient way of transferring nice properties from the Gaussian onto other measures, in that we have some property we want to know holds true for certain classes of probability measures. And we know how to prove it for the Gaussian, because the Gaussian has a lot of very nice algebraic properties. We have an explicit basis of orthogonal polynomials. We have very nice stochastic interpretations. We have the central limit theorem as a way of approximating Gaussian measures with simple descriptions. And we have something nice we know how to prove for the Gaussian, and we would like to transfer it to measures with a more general structure. And let me talk about two examples. The first one is going to be the Pancreatic inequality. So the Pancreatic inequality for the Gaussian measure states that if you can control the variance of any test function, so the difference between the average of the square of a test function and the square of the average, we can always control this by the L2 norm of the gradient of your test function. And the prefactor 1 is true in any dimension. So we have a dimension-free Pancreatic inequality. In all dimensions, we can control variance by L2 norms of gradients independently of the dimension. And this inequality has many applications. It is related to concentration of measure, in that it implies that we can control the probability of observables having some significant deviation from their mean, independently of the dimension, so for functions of many independent Gaussian variables. And this principle has many applications in statistics, for example, in model selection theory. It also has applications to rates of convergence for diffusion processes. It has an interpretation as a spectral estimate for certain generators of certain Markov processes, and we can use it to estimate rates of convergence. And what's one nice property here is that such an inequality is trivially stable by Lipschitz maps. Why? Well, let's have some measure nu, that's the image of the Gaussian by a one Lipschitz map. And let's take a centered function. So we forget about the integral of f for a minute, it's 0. We look at the average of f squared. Well, just because of the change of variable, we can write it as the average with respect to the Gaussian measure of f squared composed with the transport map. And now we have a Gaussian average, so we can just apply the Poincare inequality. And by chain rule, we can bound this by the L2 norm of gradient of f squared. But we have to multiply by the Lipschitz constant, so the operator norm of the gradient of t. But of course, if you're globally one Lipschitz, this is bounded by 1. So we still control by the L2 norm of the gradient with respect to nu. So Lipschitz maps preserve Poincare inequalities. And what's particularly nice in Caffarelli's theorem is that the Lipschitz constant is dimension-free. So we still have a Poincare inequality with dimension-free constant. So it's still going to apply to high-dimensional situations like systems of many random variables. But now the measure nu, it has a convexity property, but it's not necessarily product anymore. So in particular, this inequality applies to random systems that are high dimensional but not independent. The second application I would like to discuss is Gaussian isoperimetry. So I see. Sorry. So there is the Gaussian measure satisfies a nice isoperimetric principle. We look at some sets with fixed measure, and we are interested in its boundary measure. So what's the boundary measure? So we have some sets A. We look at a small enlargement of A, so an epsilon neighborhood. We look at the Gaussian measure of our epsilon neighborhood, and we subtract the Gaussian measure of the original sets. And then we divide by epsilon, we let epsilon go to 0, and we look at the limits. So this gives us a Gaussian surface area measure. You can think of it as a Gaussian perimeter of the set, but weighted with the Gaussian measure. And it happens that the Gaussian measure satisfies an isoperimetric inequality. So among all sets with fixed Gaussian volume, the sets with the smallest possible Gaussian perimeter are half spaces. So this is kind of an analog of the classical isoperimetric inequality, which states that smallest possible perimeters with fixed volumes are balls. Here it's for the Gaussian measure, it's a half space. And of course, we can explicitly write what's the parameter of a half space in terms of its volume. And this is the inequality from which we can rewrite if we explicitly write down what's the parameter of a half space. So given a half space with some volume gamma, its Gaussian parameter is given by taking the cumulative distribution function of the Gaussian distribution, inverting it, applying it to the volume, composing with the Gaussian density. Okay, so that's a certain function that might not look so nice stated this way, but it's quite a nice function. It's concave, for example. And we can always bound from below the Gaussian parameter by a function of the Gaussian volume. And equality cases in this inequality are exactly half spaces. So this is a theorem was originally proved by Tsirelzan and Sudakov and independently by Borel. And later on, there were other inequality proofs by Bobkov, by Bacri and Ledoux, by Barton-Moret. And for example, the Bobkov proof is very Gaussian in the following sense, and I would like to say a few words about it because it highlights kind of the specific nature of the Gaussian. In that, what Bobkov proves is that he proves an inequality for a certain inequality for a Bernoulli random variable. So a random variable that takes value 0 and 1 with a certain probability, and a very basic inequality for real values that's completely trivial. Well, not completely trivial, but it's just an inequality on R. And then says, okay, the Gaussian is the limit in the central limit theorem. So I can view it as the limits in distribution of a sum of Bernoulli random variables. And then he passes to the limit in an inequality for Bernoulli random variables. So it's a very nice proof, but it specifically uses the fact that the Gaussian measure arises as a limit in the central limit theorem. And of course, this is a very Gaussian property. So, and now what happens is that this inequality is indeed trivially stable by Lipschitz change of variables. Why is that? It's because the perimeter can only increase if we push forward by a Lipschitz map. So we still have the same lower bound with the same function here. If we replace the Gaussian measure by any measure, that's the push forward of the Gaussian distribution by a globally one Lipschitz map. So this is not the only way of proving this this result. So the Bacri and Ledoux proved this result using a subgroup proof that also works for these uniformly log concave measures. But okay, this gives an alternative proof. And this inequality is a particular instance of a much broader theory on metric measure spaces, for which the original subgroup proof of Bacri and Ledoux does apply, but for which we do not have an analog of the Caffarelli contraction theorem. Okay, so this was just to highlight why we are interested in having globally Lipschitz change of variables. And there are other similar problems where these questions arises. For example, correlation inequalities, logarithmic Sobolev inequalities. We also have the same stability by Lipschitz maps. So now I would like to talk about the proof. And the key tool in the proof I will talk about is the entropic regularization of optimal transport. So we are going to consider a penalized optimization problem, and instead of minimizing over all couplings the quadratic cost, we minimize the over couplings this cost, but we penalize it by an extra entropy term. So we take the relative entropy of our coupling with respect to a product Lebesgue measure. So relative entropy of some measure with respect to another measure is just the average of rho log rho, so of the density times the log of density. So Jan already spoke about entropy in his talk. It's a very classical functional. And so what we're going to do is we penalize the transport problem by epsilon times an entropy term. And this breaks the deterministic character of the optimizer. It's not we force the optimal coupling to have a density with respect to Lebesgue measure, so it's not going to be concentrated on the graph of some function. But it's going to be much smoother, and we're going to use this extra smoothness. And okay, so this problem has a rich history, which I will address in a minute. But before, I would like to talk about the stochastic viewpoint. And because up to lower order terms in epsilon, there is a stochastic counterpart to this minimization problem, which is the following. We consider a Nordstein-Uhlenbeck process. So this is a stochastic differential equation where we have a path in RD, we have a drift that sends us back towards the origin, and we add a Brownian noise. So this is a very nice stochastic Markov process. It has a lot of very nice properties, and one important property here is that it's a reversible stochastic process whose unique invariant probability measure is the standard Gaussian distribution. So if you start with initial data that's standard Gaussian, this is preserved by the flow. And we're going to consider the distribution of a path of this process between time 0 and epsilon with Gaussian initial data. So it's a stationary process at any fixed time. The distribution at a given time is Gaussian, but there are correlations between what happens at initial time and what happens at later time. And we consider this distribution, and we can minimize the relative entropy of the law of the path with respect to the law of this particular path. So it's an entropy minimization problem over the space of paths, and we optimize it over all distributions with fixed marginals distribution, initial distribution mu, and distribution mu at some time epsilon. So this problem is known as the Schrodinger problem. It came up in work of Schrodinger on analysis of the so-called lacy gas experiment. We will not talk so much about the physics here, but it's a nice way of regularizing the optimal transport problem because it has a very nice structure. The optimal coupling in the regularized problem is of the following form. We look at the joint distribution at time 0 and epsilon of our process. This distribution is completely explicit. This is its density with respect to the Lebesgue measure. Completely explicit formula. And the optimal coupling has the following structure. It's it has a density which is a function of both x and y with respect to this distribution, but its density is product. It's a product of a function that only depends on x and a function that only depends on y. So this is related to this structure as a minimization problem. I will not really talk about how we prove this, but this happens to be true. And its subset comes up from the dual formulation, because we can reformulate entropy using Legendre transform on spaces of probability measure. We can once again reformulate minimizing entropy as maximizing average, as a maximization problem over a space of function. And the maximization problem is the following. We want to maximize the average of the logarithm of a function f with respect to mu plus the average of the logarithm of a function g with respect to nu, under the constraints that the average of the product of the two functions with respect to r, this r epsilon here, is equal to 1. And this is the regularized counterpart to the Kantorovich dual formulation of optimal transfer problem. And what happens, and this can be explicitly proved, is that the minimal cost in this entropy regularized problem converges up to some factor epsilon to the transport cost. Is that epsilon times the infimum of entropy of pi with respect to r epsilon converges to the infimum over couplings of the average of 1/2 of x minus y squared. There are many ways of understanding this result. One is that, well, where is this y minus x squared come from? Is that if you take the log of r epsilon, the leading factor up to rescaling by epsilon is going to behave like x minus y squared over 2. It's this one here. So it really is a Taylor expansion of relative entropy up to the rescale. The leading order term behaves like 1 over epsilon times x minus y squared over 2 in the log density. And so that's kind of the, and so this was this regularization problem of optimal, viewing this Schrodinger problem as a regularized problem, transfer problem, was first pointed out by Mikami, and then popularized by Leonard and revisited by Carlier, Duval, Perret, and Schmitzer. And we can also prove convergence at the level of the optimal potentials in the dual formulation. So if we take the optimal densities for the regularized problem, we take their logarithm and we rescale by epsilon, we have convergence to the optimizers in the dual formulation. So 1/2 of x squared minus phi and 1/2 of y squared minus phi star. This was these were the potentials in the Kantorovich duality. So not only do we have convergence of the cost, we have convergence of the optimizers in the dual formulation. So we can use the optimizers in the regularized problem as a way of approximating the Kantorovich potentials. So this result was first proven by Gili and Tamanini in the compact setting. And a few days ago, Nutz and Wiesel posted an archive of preprint proving this for in the non-compact setting, and even for more general costs too. Okay, so now I will explain a bit why this is useful. And the main reason why this regularization attracted a lot of interest over the past few years is that from the numerics perspective, it's much easier to approximate these regularized potentials than the optimal transport potentials. And why is it easier? It's thanks to something called the Synchron algorithm. So because of the marginal constraints, we know that this measure here it is a coupling of mu and nu. So its first marginal has to be mu, and the second marginal has to be mu. So we can look at the constraints we get by averaging it with respect to its first and second marginals, and we get the following relationship between the two potentials, F and G. So F has to be 1 over P epsilon G, and G has to be e to the power minus V over P epsilon of epsilon, with some P epsilon an explicit convolution operator. It's an operator that's just a convolution with an explicit Gaussian kernel. And so given G, we can reconstruct F. Given F, we can reconstruct G. So this has led to the following iterative scheme, in that we start with two functions F and G, and we iterate these two relations. And we know that once we reach a fixed point of this iteration, we end up with a solution to the Schrodinger problem. We up to a multiplicative constant. Under some assumptions, these two functions are unique, and they are the only fixed points in this iteration. And it happens that this iteration indeed converges to the optimal potentials. And this seems to have been first proven by Fathi in the 1940s, and then forgotten for about 70 years and rediscovered by a few years ago by Leonard and by Georgiou Chen. So yeah, why is this useful for numerics? Is that this iterative scheme, or at least a spatial discretization of this iterative scheme, can be implemented. It's explicit convolutions, and it converges very quickly. In the compact setting, it actually converges exponentially fast. Okay, and this has led to Couture's Synchron algorithm for approximation of optimal transport maps. Okay, but the original motivation and the interest it attracted in optimal transport came from the point of view of numerics. This is not really the focus here. So what we ended up wanting to use this regularization to prove the Caffarelli contraction theorem. And so we wanted to prove that gradient of phi is 1 Lipschitz. And this is equivalent to showing that 1/2 of x squared minus phi is convex. Gradient phi is Lipschitz. Gradient phi is Lipschitz if and only if, at least in the smooth setting, the eigenvalues of the Hessian are all smaller than 1, which is the same as saying that identity minus the Hessian of phi is a non-negative symmetric matrix, which up to smoothness issues is the same as saying that 1/2 of x squared minus phi is convex. So we want to prove that this function is convex, and we know that log of epsilon, f epsilon, is a good approximates it. So what we're going to show is that f epsilon is log convex, and then pass to the limits. And why is log f epsilon convex? It's because this explicit convolution operator preserves log concavity. If you take a function whose logarithm is concave and you apply this convolution operator, you remain log concave. This is known as Prekopa's theorem. And the operator also preserves log convexity. That's just a consequence of Huggles inequality. So we have an iteration that preserves log concavity and log convexity, and we want to show that its fixed point is log convex. Well, we're almost done because of uniqueness of fixed points, where we really do expect that if we preserve this property, the fixed point is going to inherit it. We just have to show that the iteration does converge if we start with initial data that's log convex. And okay, it works if we start with nice initial data that's log convex. And this was just a modification of Forte's original proof. So we have preservation of log concavity and log convexity. So the fixed points are going to be, f is going to be log convex and g is going to be log concave. independently of epsilon, and then we just pass to the limits. So that's just the proof. It's really just a consequence of the nice properties of this regularization scheme and the fact that convolution with Gaussian kernels preserves the log convexity and log concavity. And where does the convexity of V shows up? Is that at the level of the logarithm? V is just, we just add something concave in the iteration, and adding something concave to something concave, it remains concave. So this is where the concavity of V shows up. Convexity of V shows up. So that's just that's how the proof works, really. So now I have to make a confession is that this is not how we did the proof, because the result of convergence of potentials we need in this scheme was posted on arXiv 2 weeks ago, and we did this a year ago. So what we actually did is that back then all we knew was convergence of optimal costs. And so we did one more dual reformulation and used a dual variational characterization of Lipschitz transport maps that was proved a few years ago by Gozlan and Juillet in order to only use convergence of the costs rather than convergence of the potentials. But that step of the proof is now obsolete thanks to the results of Nutz and Wiesel. So I will not say more about that one. Okay. So now I should say a few words about the general version Juan Luis asks for at the beginning. So the real version, which is originally proved by Kolesnikov using Caffarelli's method, is that we don't really need a Gaussian. What we need is something that is log convex, in that we need a density that has full supports, and the log of the density should have the minus the log of the density should be semi-concave, in that its Hessian should be bounded from above. And indeed, for the Gaussian potential, we're just bounded from above by 1. So the full version of the theorem is that if we have transport something that whose logarithm of the potential, whose potential has a Hessian bounded from above and full supports onto something where the Hessian of the potential is bounded from below by something strictly positive, the optimal transport map is globally Lipschitz, and the constant only depends on upper bounds on the Hessian of the density of the starting measure and lower bounds on the Hessian of the target measure, independently of the dimension. This square root of beta over alpha is a dimension-free quantity. So that's the general version, where we don't, the Gaussian structure does not truly play a particular role. What really matters is the nice convexity properties. And the scheme of the proof I just presented works in exactly the same way. In the iteration, the only difference is that instead of iterating Fn as 1 over P epsilon of G, we need to multiply this by e to the power minus W. But this does not break down preservation of log convexity. Sorry, not e to the power minus W, e to the power 1/2 of x squared minus W. But okay, this does not break down the nice properties of the iterative scheme. Okay, so that's the end of the proof. So just I want to raise a few open problems that we would love to know. One thing I would really like to know if it's possible to prove non-uniform estimates with this method. So 2 years ago with Maria Colombo, we were interested in proving non-uniform estimates on transport maps. And what we studied is that we transport the Gaussian measure onto some density e to the power minus V, with just V just convex, not uniformly convex. And what we expect is that the operator norm of the Hessian of phi should have controlled growth at infinity, and that it should be less than some constant times 1 plus the L infinity norm of x, something like that. This is a very optimistic conjecture. I don't know how to prove this. And I'm not really truly sure this is correct. This would be a very optimistic conjecture. And the prefactor C should only depend on the barycenter and the second moment of the target measure. And this is true in dimension 1. And we don't know for higher dimension. And what we proved is that under certain conditions with Maria Colombo, we proved not in this fully generality with extra conditions, but that the Hessian of phi up is less than 1 plus L2 norm of x squared. And sorry, not 1 dimension. So this is much worse than what we would love to see. For applications to the kind of isomeric problems I mentioned at the beginning, these are the kind of results we would need. This is not very good for these applications, but it's kind of the best we managed to prove using maximum principle. And now one thing we would love to know is if there is a way of kind of localizing this iterative scheme to get to prove propagation of non-uniform estimates on the transport maps by the iterative scheme. And the other question this raises is about proving global estimates on transport maps on manifolds or for other costs than the quadratic costs. For example, we would love to know if there is some kind of Caffarelli contraction theorem for transport for maps between manifolds satisfying some curvature conditions. For example, if can we map an n-dimensional sphere onto some positively curved manifold satisfying some condition on the dimension in some globally Lipschitz way? We don't know if this is true, but this would kind of fit well with this picture of optimal transport on manifolds, where these kind of convexity conditions I discussed are often replaced by conditions on the Ricci curvature tensor of the manifold. And then there are some questions raised about other costs. For example, one particular example of cost where we expect this kind of argument to work, not quite in the same way, but similar stuff, and nobody has done it, but something we kind of suspect something interesting should be true, is for the cost log of 1 minus x dot y, the logarithm of the positive part of 1 minus x dot y. So this is known as the reflector antenna cost. It shows up in some reflector antenna design problems. The qualitative regularity theory of this cost is understood because it satisfies something known as the Maître-de-Guerouin condition that assures nice qualitative regularity properties of transport maps. We don't know much about quantitative regularity, but something we do expect. Why do we do expect something nice is that because the duality, in the sense of Kantorovich duality, of this transform has very nice properties in the following sense. We know that the Legendre transform associated with the duality theory for the quadratic cost satisfies the following characterization. It's the only monotone involution on convex functions up to trivial transformations. But now, if you look at monotone involutions on the sense on non-negative convex functions that have reached their minimum at the origin, there are exactly two order reversing involutions up to trivial transforms: the Legendre transform and the exponential of the dual transform for this cost. This is a theorem due to Aarstein, Avidan, and Millman. So duality for this cost is very, very nice in some sense. And this kind of raises some questions. And there are kind of hints that maybe there are nice stochastic processes that played a role for these kind of transport maps. So here I talked about entropy regularization, and we had convolution with Gaussian kernels. There are some hints that maybe there are some similar stochastic transforms that played a similar role, where instead of convolving with Gaussian kernels, we should multiply with gamma distributions. These are vague hints in the literature. There is no broad theory. This is kind of vague guesses motivated by recent works of Aarstein, Avidan, and their collaborators, as well as by Pat and Wong. Okay, so that's kind of all I wanted to discuss today. Thank you very much for your attention.